folks. So, I'm making another video here for the purposes of talking about electron transitions and what happens when electrons move from shell to shell. So, in this picture, this electron is in the first shell, and the first shell is called the ground state of the electron. And inherently, all systems naturally behave in such a way that they always want to minimize their potential energy. You know, when I drop this object, you notice it falls down, right? And if you think about this in terms of potential energy, this object naturally moves towards a state of lower potential energy. Water flows downhill, trees fall over, etc., etc., etc. All systems naturally tend to move towards a lower energy state, and atoms are no exception. This is the lowest energy state. So if this electron were up in a higher energy state, it naturally wants to come back down. So we would say that, you know, this electron would fall from the n equals 2 state to the n equals 1 state. Now, let's talk a little bit about, well, how would it get to the n equals 2 state to begin with? In order for this electron to get up to the n equals 2 state, it has to acquire extra energy. It's got to go from minus 13.6 EVs to minus 3.4 EVs. So what has to be added to that, I believe, is, I think, 10.2 EVs of energy. So this electron would have to acquire the difference in energy between these before it can jump up to the higher energy level. One mechanism for that to happen is if this electron absorbs a photon. So what can happen is, picture a photon kind of buzzing through here. And this photon, remember, has a certain frequency and it has an energy that depends on that frequency. And if this photon has just the right energy, the energy that is the difference between these two, then the electron will absorb that photon and it will move up to a higher energy state. Right? Then the photon, we would say, is, well, basically gone. But then the electron is kind of in an unnatural state. This electron naturally wants to move back to its lower energy state. So when it does so, it moves back from the n equals 2 to the n equals 1, it'll give up a photon. And the photon that it will give up will carry the same energy it had to begin with. So this is a little bit about how electrons work, and they go from, these electrons can go from orbit to orbit or from shell to shell. When they're absorbing photons of the correct energy, they will jump up a certain amount, conceivably further, and then they'll naturally want to fall back down. So when the electrons absorb photons, they move up to higher energy levels. When the electrons move back down to the lower energy levels, they give those photons back up, or they can give photons back up. Now, let's talk about this electron when it goes from the n equals 2 state and it falls down to the n equals 1 state. When it does so, it will give up a photon, and that photon will have a certain energy. Let me call that EPH, for energy of the photon. And the relationship here between the energies is a very simple arithmetic type of relationship. Whatever energy I started with has to equal whatever energy I ended with plus the energy of the photon. So I could say, all right, the energy at state 2 has to equal the energy at state 1 plus the energy of the photon. And I can write that out mathematically like this. So the energy of the photon is equal to the energy at state 2 minus the energy at state 1. Right? So the photon energy is equal to the difference in energy between these two states. I have these numbers already written up here. The energy at state 2 is minus 3.4 EVs minus the energy at state 1. When you're doing these calculations, you've got to be very cautious of plus and minus signs. The energy at state 1 is minus 13.6 EVs. And remember, when you subtract a negative, that becomes a positive value. So what we end up with is, I believe, positive 10.2 EVs. Okay. So the photon will leave with an energy of about 10.2 EVs. Okay, now, remember that the photon energy depends on the frequency. So what we're going to do now is we're going to calculate the frequency of that photon using this relationship back over here. Energy of a photon is equal to Planck's constant times the frequency. Now, the first thing you got to notice is when you look at Planck's constant, the units, 6.63 times 10 to the negative 34th joule second. Written like this, to use this relationship here, we need the energy in joules, not in EVs. So in order to convert or to take that energy and figure out what frequency or what color that photon is, we're going to first have to convert that to joules. So here's what it'll look like. 10.2 EVs times, now we're doing a unit conversion. Here's a little review about unit conversions. We're going to multiply by a factor, and that factor is going to have EVs on the bottom, joules up top, so that the EVs cancel. And 1 EV is equal to 1.6 times 10 to the minus 19th joules. I'm sorry that got so small. So when we go ahead and do this calculation, what I get is 16.32 times 10 to the minus 19th joules. Now that's not generally standard scientific notation, but that's all right, no problem. So now, I know the energy of this photon is 16.32 times 10 to the minus 19 joules. Now what I want to do is I want to calculate a frequency, and I can do that using this relationship. The energy of a photon is equal to the Planck's constant times the frequency. So the frequency is going to equal the energy divided by Planck's constant. And the energy is what I just calculated. 16.32 times 10 to the minus 19th joules divided by Planck's constant, which is 6.63 times 10 to the negative 34th joule seconds. Let's see what we get out of that. Okay, I get 2.46 times 10 to the 15th power. Doesn't seem right to me. Taking 10 to the negative 19th, dividing that by 10 to the negative 34th. Yeah, I guess it looks right. Okay, so there's the frequency of that photon. And now what I'm going to do is I'm going to take a moment and I'm going to check on the electromagnetic spectrum, which we talked about in one of my last videos, and I'm going to look up that frequency and just see where that falls within the EM spectrum. Alright, let's see here. Got to find the electromagnetic spectrum in my book here. Have that already turned there. Where is this thing? Oh, there it goes. In the wrong chapter. Alright. Sorry about this. Frequency of around 2.5 times 10 to the 15th. Looks like this is putting this in the UV region, or in the ultraviolet region of the electromagnetic spectrum. So, take a little time, look up the electromagnetic spectrum, verify that frequency ends up in the UV region, 2.46 times 10 to the 15th hertz. And hope you enjoy it.